that means that little vertical filled in black rectangle indicates the end of the proof. So different authors, different conventions, but a lot of modern authors seem to have converged on this one, just a hollow square, so the end of proof symbol. Okay, let's do another example of a proof. This one's fairly easy, this one is a bit harder. Yeah, now if A and B are, A and B are integers, so I assume you've done some mathematics. This symbol here sort of looks like a little E, Greek E, or epsilon in the Greek alphabet. It's a symbol that means belongs to. Right? So belongs to, and this Z here, that's a capital Z, or Z if you're English. It's a symbol for a set, and it's the set of all integers. Now, what are the integers? Well, 0, plus or minus 1, plus or minus 2, and so on. Okay. And while we're at it, let's do another commonly used symbol, N, capital N. That's the set of the natural numbers, like the elementary counting numbers that little kids in kindergarten use, like 1, 2, 3, and so on. So they're the natural numbers, 1, 2, 3, so on. Okay? So N is the set of natural numbers, Z is the set of integers. Okay? So saying here, if A and B belong to Z, that's telling you that these two numbers here, A and B, are integers. Okay? So if A and B are integers and even, then their sum is also even. How to prove that? Well, if A is even, you can write it in this form, 2n. So, and similarly for B, if A and B are both even, you can write them in this form. So M and N also belong to the integers. Okay. Well, the product, the sum. So if we add these two, so A plus B will be, well, 2m plus 2n. And you can rewrite that as 2 into m plus n. Okay. Now, whatever this is, if it's odd or even, doesn't matter. If you multiply it by 2, you'll get an even number. Right? So this is even, has to be even. Doesn't matter what m or n are. A and B are even, you're told that. See, if A and B are even, then A plus B, the sum, is even. We've just shown that. See, A plus B is an even number. Okay, so that proves that. Fairly simple proof. All right, let's get a little bit harder. So what I'll do now is introduce a very useful technique in proofs in pure math. It's called proof by contradiction. And the Latin, the old-fashioned name for this kind of proof is abbreviated to RAA. And I'll write that out. It's again Latin. So RAA. That's reductio ad absurdum. Okay. Now, if you translate that into English, it means reduction to absurdity, meaning a contradiction. So a contradiction is something like P is true and not P. This wiggle tilde, that means not. So P is true and not P is true. That's a contradiction. You cannot have both. Right? That's not logical. So a proof by contradiction involves getting something true and not true. It involves creating a contradiction. So let's do some examples of proof by contradiction by RAA. So I'm wondering whether to give you the general theory behind this kind of proof first, or to just well, I'll start with a concrete example and illustrate the general principle later, and give you this proof. Let's prove that square root of 2 is irrational. We'll try to prove that. That's the exercise. Now, there's a little bit of history, interesting little story behind this. You go back 2,000 years into the time of the ancient Greeks and Pythagoras, the famous Pythagoras of Pythagoras' theorem. He believed, he had a kind of mathematical cult, sort of quasi-religious beliefs that the universe was basically, what's the word, dictated, controlled by numbers, by integers. Now, the Greeks knew about rational numbers. What's a rational number? So a rational number is of the form A over B, where A and B belong to the integers, with one exception. B cannot be 0. Right? That's forbidden. If you're dividing by 0, you get infinity, and it's so just not defined. Right? So a rational number is defined as A over B, A divided by B, where A and B are both integers. Right? They belong to Z. Z is the set of all integers, with one exception. The B here cannot be 0. I mean, the A could, but not the B. It cannot divide by 0. Okay. Now, those are rational numbers by definition. So, by definition, usually the symbol in pure math is to put like 3 little bars like that, three lines. It's sort of like an equal sign, but with an extra bar. So, if you see 3 like this, it means is defined by. Right? It's the definition. So, if you have something of I don't know, P 3 bars Q, then what that usually means is whatever's on the left-hand side is defined by whatever is on the right-hand side, right? So this symbol, useful symbol, is so the definition of P is Q. Definition of what is on the left-hand side is given by what is on the right-hand side. So that's the definition symbol. All right. So that's a definition of a rational number. Yeah, I'm definitely going to have to find a better way, a more effective way to rub out. This is not clean enough. Okay, so let's prove that the square root of 2 is an irrational number. In other words, it's not of this form, not of the form A over B. Right? Where A and B are integers. So it's the ear. That means like not rational. So how do you prove that? How do you prove that root 2 is not rational? Like if you have a right angle triangle, and here's where the history with Pythagoras came in. If the base and the altitude are both magnitude 1, then Pythagoras' theorem says the hypotenuse here is of length root 2. And you cannot find numbers, integers A and B for root 2. Now, how do you prove that? How do you prove that square root of 2 is irrational, not rational? How do you prove that? Well, we can use this particular proof technique, proof by contradiction, or RAA, reductio ad absurdum. So let's, and the way we do it is to assume the opposite. So let's assume that root 2 can be written as a rational number, right? That is, i.e., assume